from today, we're going to look at classification. We're going to start to cover chapter 8. And even though the book put a lot of material in chapter 8, based on my experience teaching this class in the past 2 years, it's impossible to cover all the material in an adequate manner in one class. So I'm going to split chapter 8 into 2 parts. So the first part, we're going to cover the basic concepts of classification as a machine learning and a data mining task. I will cover decision tree induction, which is, as probably all of you are aware, a very classic but still quite robust approach in use today. Then we're going to cover model evaluation and selection. When we have learned using the training example and learned some models, we want to know how good the model is. So those are the essential concepts that we're going to cover today. Um, um, Next week, we're going to cover 2 other methods, Bayesian classification and rule-based classification. And we're going to talk about a variety of techniques to improve classification accuracy. And we're going to talk about imbalanced data problem and how to address those. Okay. So learning objectives for this week. Student, after this chapter, you should be able to describe a basic decision tree algorithm in detail. So every step, I think this also is a homework problem that you need to describe what a decision tree algorithm does. Similarly, random forest is an ensemble method based on decision tree. So you should also be able to explain the random forest algorithm and why it is an ensemble method. Random forest in practice, random forest is used in place of decision tree because this algorithm has been proven in so many application settings being robust. Then you will need to be able to understand, list, and explain a whole variety of performance measures, including accuracy, precision, recall F measures, true positive, false positive, sensitivity, specificity measures, and you need to learn how to plot a ROC graph. The idea behind ROC graph can be used to plot other performance evaluation method graphs. So it's essential for you to have a good grasp of the ROC graph. Lastly, you need to be able to conduct paired or non-paired t-tests. I trust most of you know how to do that already from your other statistic class. But in machine learning and data mining, I really want to emphasize this. Because our algorithm can perform very differently depending on what training example you provide. Therefore, the performance of an algorithm cannot be determined by a single run. Therefore, t-test or other statistical estimate of a true performance is very, very important. I know in some disciplines, t-test has been banned, saying it's been overly used. However, in machine learning, conducting statistically significant tests on performance are key. Even though some, shall I say, lower end publications don't include those, that's totally bad practice. So it's don't be influenced by those bad practices. Always keep in mind the performance of any machine learning algorithms cannot be reliably represented using a single value. It has to be a set of values that we can actually to tell whether this value represents the true performance or not. So now let's get into the content, basic concepts. So some of those are review, but I learned from a student of mine that review is important. I used to not liking reviews because I feel like it's a waste of time. You already told me this a week ago. Why do you have to tell me again? The reason that sometimes we do reviews is because some of the concepts are really important. So supervised and unsupervised learning, we're talking about classification this week. So classification is a supervised learning. How can we tell supervised learning from unsupervised learning? Um, they are differentiated based on what information that's provided to the learning algorithm from an external source. So a lot of times in machine learning or data mining, the external information that we provide to a learning algorithm is the training data. So we tell the system whether this data is true or false, this piece of observation belongs to this class or that. That's the extra information um, label that we provided to the algorithm. This extra information, it could be labels, it could be something else. It does not it does not need to be labels all the time. As long as there's external information that we need to provide to the algorithm, and that affects the algorithm performance, um, the algorithm can be considered as supervised because there's external help. On the other hand, the unsupervised learning, it does not require, besides the hyperparameters, it does not require any additional information. It's the raw data that you feed into the system. The algorithm going to produce mine and learn something from the data itself. So one example we have already, actually we have seen two examples before. We look at attribute-oriented induction, where you might have given a few thresholds to do binning. Other than that, the system conducts the induction automatically. Association rules, we didn't give in the system any information at all. The algorithm going to find associations in the data set. Later, after we complete our learning on classification, we're going to look at clustering, which is another unsupervised learning, where again, we only need to provide some hyperparameters to the algorithm, and the rest of it is done by the algorithm itself. It's completely based on what the data tells. It's used to discover useful patterns in the data set. And here, the supervised learning will give us more information than just what the data presents. It actually not only, so as compare the classification methods to clustering methods, the supervised method not only group things together, they also apply labels to the observations. So the new data is classified or a label being attached to this new observation based on this model derived from the training set. Okay. It's not deciding whether an algorithm is supervised or unsupervised is often quite easy, but there are a few cases that debates might occur. For example, we have a special kind of classification called one-class classification. So this classification is to find a description for a single class. In vast majority of times when we perform classification, we always have two class or more than two class. For example, the stock price might rise or might drop. So there's two classes. But there is a special kind of classification method. It's one class classification. We're going to discuss this in the second half. In chapter 9. So this, depending on how you use it, it can be seen as a unsupervised method. It could also be seen as unsupervised method. So there's some slight complexity in some special situations. But in general, that we can tell whether our algorithm is supervised and unsupervised by looking at the labels that we provide to the algorithm, whether we provide labels to the algorithm. Okay. A second slide, again a review slide, talking about classification. As a prediction problem, classification as one type of prediction problem. So recall earlier we mentioned there's two group of tasks that we often can put a mining tasks into. It's either a descriptive mining task or predictive mining task. So here we're talking about prediction because we're predicting class labels for observations. Another group of prediction problem is numeric prediction. Because vast majority of the numerical prediction use regression methods, so we also use the word regression as a synonym to numerical prediction. But also I want to mention that logistic regression classify things into two binary decisions. So it's considered as a classification problem rather than a numerical prediction problem. And we have mentioned earlier, numerical prediction problem predicts continuous values, and the classification methods predict nominal values, class labels. In general, classification problem is more widely used because many problems can be represented as a classification problem. Lots of what, how, and why questions can be modeled as a classification problem. So if you have a set of reasons in why this happens, and you can model this as a one classification problem, and their classification label going to be one of the reasons that you're trying to study. So why problems can also be modeled as classification problem. Regression is useful when you actually have numerical values need to be predicted. The measurement, how can we tell if the system is performing at a desired level, are also different. Classification performance is measured by the goodness, by the correctness of the classification, by comparing the labels predicted by the algorithm to the labels that's provided by human or other reliable sources. Regression, on the other hand, because there's not a label, there is a real value. Therefore, the performance of a regression numerical prediction problem is measured by the closeness of the predicted value to the true value. So two typical measures that we use is mean squared error or mean absolute error. In this class, we have lots of examples on classification, and the book also seems to have a stronger emphasis on classification Just pick. So I don't want you to forget that regression is a numerical prediction problem, and the goodness is measured in a different way from the classification methods. But we will not spend a lot of time talking about regression. Much of the regression methods requires to construct mathematical models, which is kind of different from all the other machine learning algorithms that we discussed in this class. So many applications, we heard that so often, so I don't think I want to spend time on that. Earlier we talked about, we compared classification problem versus numerical prediction problem, and now we're going to zoom into classification as one key group of machine learning and data mining tasks. So classification is a two-step process. It involves two steps. Step one is model construction. So it's an inductive process in the sense that we use training examples. We feed the system a lot of training examples for the system to construct a model. This model can be represented as a classification rule. It can be a decision tree. It can be a mathematical formula, as we're going to see, for example, support vector machines give you a mathematical formula. So the model can be represented in any way, in any form. The goal of this model is to be able to classify or label new observations. Okay, so this is an induction process. So here, the input to we call a classification algorithm a classifier. So the input to a classifier are the tuples or samples or observations and their labels. Okay. So the set of tuples or samples or observations used for model construction is called the training set. And also, we might use part of that training set, or we might get another part of labeled set and use that to evaluate some models that we learned currently to see how well they fit on the training set. And we tune the model's hyperparameters. And those data sets are called validation sets. Okay. The training set and the validation sets are from the same labeled set. So you will have some humans or crowdsourced places to get your labeled data set. You will divide those labeled data set in two main sets. One is that may be used for training or validation purposes. They could be further divided into training or validation sets, but that's the one set. The other set is the test set. So here I put a note there, the training and the validation sets are not the same as the test set. The test set is independent from the training or validation set. Okay. I'm going to have a little illustration done in 2 slides to consolidate this idea of training, validation, and test. But so at this moment, I think you need to understand training and the validation are the process that you will perform to construct a good enough model. Okay. And then you're going to perform test on a different test set. Okay, so that's once we have the model constructed, we're going to move to step 2, which is model evaluation and the final use. This is the induction process where we have the model. Now you can feed the model same to the model should cover the phenomena that we wanted to process. So when you have new observations fit into the model will be able to tell you, I think the label for this observation is such and such. Okay, so this is the induction process. So this is where when we actually use the test set, which is independent of the training and validation sets, obviously, because you will never want to train a model and then use the same data to evaluate its performance. That doesn't do any good to you, right? It just encourages overfitting. Overfitting is a phenomenon that the machine learning algorithm can work almost perfectly on training example, but cannot perform on a different similar data set. That's not what we want. What we want in machine learning and data mining is to train a model that's robust. That's why I mentioned robust so many times, and I said random forest is more robust than a decision tree. Therefore, random forest, almost in practice, you no longer read any system built using a single decision tree. It's all if a decision tree used, it's random forest. Because it's robust. It is not. If the data was trained on this subset of the labeled set, it would perform roughly equally well on the other set of the labeled data if they're coming from a similar observation pool. Okay. So here we emphasize that test has to be independent. In practice, for example, in my own project, we will have experts to label the data, and then we will seal up one portion of the test data for test, maybe 10% or 20%. We sealed it up. Our developers will never have access to this test set. It's fully controlled by me. So once the developer used the validation and training methods, and he did all those tuning, and we're going to talk about tuning in this class too, and performance enhancements. And after he did all of that, he said, okay, I'm confident the system should perform at this level. This is the time I'm going to take out the test set. I'll say, let me verify if the system really performs at the level that we expected. So this test set is totally independent of the training and the validation set. My algorithm, my PhD students or me, myself, when we need to do a training task, we always put test set in a secure location that whoever's developing the model will never have access to this test set until he's confident that the system has been validated using the process that we described here. Okay. Okay, after the final test is done, then we can use this model. We call it trained model to classify new data. So graphically, let's review the process we have discussed verbally. So we have training validation data. Those are part of the labeled data. We use this to construct classification algorithms, and we evaluate performance multiple times using the validation process, and we create a classifier, which really is a model that this if we're using if you're using decision trees, then this classifier going to produce some rules like if rank is professor or years is greater than 6, then this professor is tenured. Okay. So here the data set looks like this. We have 1, 2, 3 attributes. The attributes are also called features. And we also have a special column called class label. So here our label is whether this individual is tenured or not. Okay. this is the model construction and validation process. We use the training example to construct the model. We actually, in this process, already did multiple rounds of validation that we feel like, okay, this model is good enough. And then we do the final test. This is independent labeled data set from the training and the validation set. And we use the test set to evaluate the classifier if this final unbiased evaluation. So unbiased means that this test set is independent of the training or validation set. Okay, so only when you have a test set that's completely independent, different from your training and validation set, you can claim that your final evaluation is unbiased evaluation. So then you have the final classifier, and this can be actually, maybe it can be implemented in a web browser and in a web application that can be deployed into the real world and start to classify unseen data, new data. Okay. So if you read machine learning literatures, classification algorithm publications, there might be some confusing phrases used there. For example, I've seen many articles use the word development set. This may be a culture bias because I say development set, this term, in publications that's with authors from another country a lot of times. So a development set is part of the training or validation set and from the test set. And some articles that only report development of certain algorithms, they don't have a test data set because it's not meant for the future, for the immediately deployment in the real applications. It's just reporting this algorithm. So you will see they often have this training and validation processes being reported. So yeah, earlier in even some textbooks, the validation data set in the k-fold cross-validation process were called the test sets. So this is confusing. This test set is really validation set, not the final test set. So I make a note here. So when you read the articles, research publications, you have a way to help you to pin down what really those data sets are. So this is my graphic description of the whole process. So we start when we have a data set and we know we have a prediction, a class label prediction problem. Immediately, we need to decide which of the learning or which of the classification algorithms we need to use. We have decision tree, we have naive Bayesian, we have Bayesian network, we have support vector machines, we have artificial neural network. There's so many classification algorithms that we can choose. So which one of those might give us good performance? So we'll use training example to select among all those possibilities. We run training example with those algorithms and decide which one performs better. And that will give us, then we were going to focus on this particular, for example, say we pick the decision tree. Then we're going to tune this decision tree, use validation data set to find hyperparameters. Okay, so now hyperparameters. I think this is probably the second or the third time I mentioned hyperparameters. So what really is a hyperparameter? How is it different from parameters? So in the context of machine learning and data mining, we often use the term hyperparameters to refer to the parameters that's provided by the user to the system. And we use the term parameters to refer to the parameters or the arguments or weights or anything the computer, the algorithm itself learns. So, for example, in a neural network, we need to tell the algorithm how many layers of the nodes we want in this network. So this is the hyperparameter. And then, because that's what we tell the algorithm, we said, okay, build me a 5-layer network. The algorithm going to start building that 5-layer network. In the process, the algorithm will learn the weights for each every node in that neural network, and those are the parameters that the algorithm learned. Okay. So the hyperparameters are the user configurable parameters that's provided to the system. And we need to find a lot of algorithms needs hyperparameters. And for some algorithms, they're very sensitive to the selection of the hyperparameters. So therefore, picking the right hyperparameters can be a task. So the way that we do that is to use validation sets. We divide the same labeled data set that we might have used for training, and we divide it into multiple subsets and use it in multiple rounds to find the best combination of hyperparameters and to eventually learn hopefully the best model that we can learn. If so, after the validation steps, we're going to do multiple rounds of test. If we evaluate the system, if the system is good, okay, then we can do the final test, right? So this is our test data set, the final evaluation, unbiased performance evaluation. If we also passed this and the performance is still good, then we're happy. The system is ready to be deployed. So this is our happy story. In reality, a lot of times this probably doesn't happen that smoothly. We will validate this the model multiple rounds, and most often we'll find initially it's not very good. So we have to come back here to pick a different set of hyperparameters, maybe a different neural network architecture to improve the performance until it is good enough for the final test. In the final test round, if we did our work well here, often the test round is just a confirmation. However, it could also happen that the test turned out to be really bad. Recall our example of using the algorithm is learned to find tanks in forest. The learning algorithm was performing greatly on those training and validation set, but when they moved to a different setting, the performance was dropped dramatically because the algorithm was learning the raindrops, not the tanks on the training examples. Well, anyway, so if occasionally when this final test proven to be not good, then we have to go back to the very initial step to reconsider, did we choose the right algorithm? Did we further, what are the problems that prevented us from learn the model? It's not the model has problem, it's the training example has problem. It's a combination of different multiple source issues. But anyway, I think at this time you should know the process and really understand the training, validation, and test set. What are they, and what their purpose are. Okay, so now we can, after talking about those basic concepts, we can look at decision trees. I need to stop the video. It's already too long. I will start another video to talk about decision trees.